So welcome back. Last time we did these two equations. We did if you like, the linear version, which involves which involves basically lambda and velocity, wavelength and velocity, and then the angular version, which involves the angular wave number and the angular wave frequency. So let's do an example of this. Sine wave has a magnitude of 3 meters, so has an amplitude of 3 meters, so that's going to be 3 meters from there to there. So A is equal to 3 meters. It has a wavelength, so lambda is equal to 2 meters. It has a velocity, which equals 4 meters per second to the right. That's important. And it wants to know what the y displacement is for x is equal to 5 meters and t is equal to 1.2 seconds. So I start off and somewhere down here and somewhere in time and x, I'm trying to find out what this value is. And I use a hint here, then frankly on the test you won't have a hint. It'll be sine 2 pi over lambda x minus vt. And I can leave it as minus vt because it is moving to the right. So y is equal to, I'm going to say 3 sine 2 pi over 5, because my wavelength, I'm sorry, 2 pi over 2, because my wavelength is 2, times 5 minus my velocity is 4 times 1.2. Let me just double check that. That's right, that's right, that's right, okay. So y is equal to 3 sine, that's pi, and this is 5 minus 4.8. So y is equal to 3 sine 0.2 pi. So I come to my calculator. And what's the first thing I check on when I get my calculator? I got to do something with trig. Yeah, check my mode. Check my calculator's on. And I look and I see I'm in radians. And so then I go, well, this is going to be 3 times, I can do it. 3 times the sine, got to be a little bit careful here, 0.2 times pi bracket, bracket. And I'm getting 1.76 positive. So y is equal to 1.76 meters positive because it is above the equilibrium position. So mathematically straightforward. There's a little bit of a wrinkle there. If you're not careful, sometimes you can get the wrong answer because of the calculator issues. We'll go through that. Same again. It's just I'm giving you other information. So now if I give you the amplitude and I give you the wave number, the angular wave number, so I just gave you K, I gave you A, I give you the angular frequency, so there's the omega, I give you the displacement, there's your x, and there's the time. So I'm going to say A is equal to 4 meters. I'm going to say K is equal to 2.3 rad per meter. I'm going to say angular frequency, omega, is equal to 1.7 rad per second. I'm going to say, what is the y? I know my x is equal to 2 meters. I know my t is equal to 3.5 seconds. And for this I say, well, y is equal to A sine kx minus omega t. And y is equal to, it is travelling to the right. A sinusoidal wave has an amplitude that, there's a frequency that, what is the way? It doesn't actually say, and I should say that. So I'm going to assume travelling to the right, because I want to use that negative sign. If it was travelling to the left, I'd make that positive. So watch out for that. And then I'm going to say that's 4 sine 2.3 times 2 minus 1.7 times 3.5. Bit of a pain here. 4.6 minus, what's 1.7 times 3.5? 5.95. So y is equal to 4 sine 4.6 minus 5.95 is equal to minus 1.35. So then I come along, I go clear, I go 4 times sine bracket minus 1.35. And I'm getting minus 3.90. That just means that it's below the equilibrium position. So, not so bad. Know those two equations, know how to use them. Watch out. The most common mistake is that people, it'll be going towards the left and people will still use the negative sign. So watch out for that. Let's go back a little bit to this velocity versus, v equals f lambda. I can play some games with it now. If I remember that f equals 1 over period, then v equals lambda over period t. This is a bit harder. If I remember that lambda equals 2 pi over k and f equals omega over 2 pi, the 2 pi's cancel. I get v equals omega over k. I know that really well. That's trivial to derive. I can derive that one though, because I know that omega equals 2 pi f, and therefore I know that k is equal to 2 pi that, and I can figure everything out from there. So with a little bit of finagling, I can figure that out. I don't remember that. I can figure it out. And the other way I can get it actually is, let's have a look. We have, what is this one? Radians per second over radians per meter gives me meters per second. Yeah. Cool. Again, let's play a little bit more. So now we want to do, let's figure out what the instantaneous velocity of this little point on my wave is. Well, just differentiate it, This is equal to minus omega a cosine kx minus omega t. And you want to know the instantaneous acceleration, just differentiate with respect to time again. We just differentiate with respect to time, both times. This is a partial derivative because what? It's got two variables in it. Yeah. So just differentiate. In truth, I don't tend to ask those so much. I don't know why. I just, they're not practiced so much in the homework and all that. But those guys there are practiced. These guys are practiced a lot. So I figure if you know those, you can figure out the others. Consider a transverse wave pulse traveling along a tight string. Intuitively, we would expect the wave speed to increase with the string's tension and decrease with mass. Mass is inertia. Things get more sluggish. In fact, v equals the square root of t over mu. Mu is the mass per unit length. This is in kilograms per meter, and this is in newtons. And And the square root sign you couldn't necessarily predict. Actually, there's an interesting point on that as well. Let's have a look. This is kilograms meters per second squared. That's force, yeah? And we're dividing that by kilograms per meter. So this is kilograms meters per second squared times meters over kilograms. So the kilograms goes, that's meters squared per second squared, and that equals velocity squared. Does that make sense, doesn't it? Well, it's bound to make sense, but I never thought about, I can just finagle it that way. We do this in a lab. Okay, so we've done this about reflection on a wall. We talked about if it's a fixed end versus a loose end, and it's very important. This is kind of like the similar, basically. If you're going from a light medium to a heavy medium, could be optically light and optically heavy. I'm not sure know what that means, but that's. Then I will get some transmission, but some reflection, but mainly transmission. If I'm going from a heavy medium to a light, I'm sorry. You'll always get transmission, you'll always get reflection, but what you get is the bit of reflection is inverted. Because it's almost like that end is fixed. You're going from something light to something massive, a thin string to a thick string. It's almost like that end has more inertia. And so it's like it's a fixed end. And so what you get reflected, you get a little bit reflected, not a lot, but what you get reflected is inverted. There's a phase shift. But if I'm going from something heavy to something light, then you do get reflection, but it's going to be without being reflected, because it's almost like this is a loose end. Because the light end, it can reflect, it can respond very quickly because it's a light string. And the analogy would be glass with a reflective index, an optical system with changing reflective indexes, or it might be wire with different resistivities. So they're the electrical and the other analogy. This is again an exercise in using general physics. We say, well, we know that elastic potential energy is that. Let's substitute in. So we say, well, we know that V equals square root of K over M. So K equals, wow, I just messed up there, omega. Am I right on that? Omega equals K over M. So we know that K is equal to omega squared times M, so we can substitute in omega squared times M. And we can say it's the mass per unit length, mu times the length. We can go to the limit. In the limit, we don't have deltas, we have D, so the change in energy and the change in length, so it's like the instantaneous. And let's have a look. We have that there, we have that there. We need y squared. Well, y we just calculated, didn't we? We just did that. We saw y before. We got to square it. Spread it all out. And then for time t equals 0, that goes away. And so we get this, and then we say, well, let's integrate this over one wavelength. So we're going to integrate this from 0 to lambda. And there's a identity in there that I had to look up in a book. But anyway, and that's why I don't, it's like you do it once and then you remember it. And we get this. And let's just stop for a minute and say, well, what's this saying to us? In one wavelength of a wave, I have an energy which depends on the wavelength. If I double the wavelength, I expect twice as much energy because it's twice as long, yeah? So that makes sense. Amplitude squared, we saw that before when we looked at oscillations. The energy tends to go with the amplitude squared. Frequency squared, we saw that with the oscillations as well. And the mass per unit length, well, yeah, it's more inertia, more mass, more energy. So it's linearly with mass per unit length. And the 4, who knows where the 4 comes from? It comes out of the derivation, yeah? So although I don't remember that, and I don't expect you to remember that, I expect you to be able to work with it because you know what the symbols mean. Okay. And I expect you to kind of like get the physics out of it. You know, oh look, yeah, if I double my wavelength, I expect twice as much energy in my wavelength. If I double the frequency, I expect 4 times as much energy because it's squared. If I double my amplitude, I expect 4 times as much energy. Just make sure you get the physics out of it. And also recognize we can do it. This is kind of cool. This is general 1, this is physics 1, and I'm getting some really valuable stuff out of this. How much energy can I have in a wave per wavelength? This is how much you can get. If I use a heavier, more massive string, I can store more energy. If I double the frequency, I can store 4 times as much energy. If I double the amplitude, I get 4 times as much energy. So you can optimize things. Yeah.
Forgive me. So, like you said, double the wavelength, double the energy.
Yeah, that's what that's saying. So double the amplitude. I'm sorry.
Double the amplitude.
Yeah, yeah. Double the wavelength, double the energy. Yes. And here's the equivalent for the kinetic energy. And I think the book used to do it the way I'm doing it, and the book switched or something. But they're the same, and they've got to be the same, because mechanical energy, you go from kinetic to mechanic to spring potential. You store the same amount in either case. And add them 2 together. So again, well, this is our mechanical energy, this is our kinetic energy, and before we had our spring potential energy. So we can work out how much mechanical energy we can store in a piece of wave traveling down a piece of string. That's kind of amazing, really. So this bit, frankly, is an example where the book tends to put equations in for the sake of putting equations in. We know from physics 1 that power is equal to the energy over the time, yeah? So if you know the previous equation, you can get this equation. So well, let me take that back a little bit. So I have this, and I divide it by the period. 1 wavelength takes 1 period to pass a point. So that's the wavelength over the period, which is velocity. And so now I've got a little bit more insight. My power goes with the amplitude squared, it goes with the frequency squared, it goes with the mass per unit length, and it goes with the velocity with which the energy has been delivered to you. Meters per second, I'd expect the power to go like that. So from my point of view, I just got to be a bit more careful. When I was doing the equation sheets, this was all fair game. But I didn't ask that many questions about it. Now that I'm not doing the equation sheets and it has to be in your head, I got to just decide, you know, we'll have this and we won't have that. And so the decision I made on these bits is, you don't have to know that equation, you don't have to know that equation, you don't have to know that equation. You don't have to know this last equation, but if I give you those equations and ask you to interrogate them, I expect you to know what they mean. So you can't just put an X over that whole chapter or that whole section and say, I don't care about this. You're still liable for the understanding of it, you just don't have to remember the equation. You know? And the last thing is, I just show you this and say, and we put stuff together and we get this wave equation, which is and all I do is show you it. I don't ask any questions about that. Okay. Maybe I should, but, you know.
So
cool.
I understand how a wave can be kinetic, but I don't understand how a wave can be potential.
A spring potential, how the wave can be potential. Or because it's well, let me stop this.